Okay. Is this thing working? Hello. Okay, first off, is anyone from Lego here? Oh. That's good. Okay, thanks very much for coming. First of all, good morning, everyone. Have you had a good conference so far? Yes, sir. Good. Okay, so much like yesterday, I talked about my journey, I guess, in terms of software architecture and things. This is about another side of what I've learned over the last, whatever it is, 27 years or so, which is about how to deliver software most effectively, I think, or more effectively, or how to deliver work, in fact, more effectively. I first did this talk 10 or so years ago. And the reason I put it together is because we did some work for Lego. So I worked for ThoughtWorks, and we were asked to help Lego out a long time ago with a massively multiplayer online game that they were building. I think it was the precursor to Universe, if you remember that. And the reason we were asked to help out is quite simple. Essentially, the game was, there's an open world which you would wander around in, much like the single-player Lego games. If you played those, you do stuff, collect bricks, and then in your sandbox, you could build cool structures, and then you could publish them, and all your friends could see them and play with them as well as you, right? In the open world. So sandbox, you build stuff, publish to the open world. Now, the problem is, if you're a child, or if you're specifically a little boy between ages, there's one thing that you try and build first out of Lego in your sandbox. And they're things that you probably don't want all the other children seeing, right? Essentially, there was lots of genitalia being built in this game, right? So we were asked to help with performance tuning of the detector for these structures. This is true. This is actually true. I'm not joking. So I had two of my colleagues. They went to Billund. Have you been to Legoland? People been to Legoland? Anyone stayed in the hotel? A couple of people stayed in the hotel. I've stayed in the hotel in Windsor in the Legoland UK. It's great. We go every year, actually, me and my son. It's not somewhere where you would normally put up two consultants, shall we say. It's basically a hotel made of Lego, and you come down for breakfast, and it's unlimited ice cream. Amazing. But, not when you're on your way to a day's work. The sugar rush kind of kills you. So about 10 years ago, as I say, we did this work, and as a thank you, at the end of the engagement, our clients in Lego, they took my colleagues to the store in Legoland. They said, is there anything here you sort of like the look of? And it's like, people in a candy shop, right? For men of a certain age, or people of a certain age. So they saw this thing, the Millennium Falcon. The Millennium Falcon, the Ultimate Edition, had just come out, the first release of it. At the time, this was the largest Lego set that had ever been made. And they said, we quite like the look of that. And about 3 weeks later, in the London office for ThoughtWorks, turned up the Ultimate Edition Millennium Falcon, along with a model of the London Bridge as well. But I'm not talking about that. So this is the story, essentially, of how me and a few colleagues, over the course of a Christmas holidays, if you like, put the Lego Millennium Falcon together. It's not just that. I'm going to try and illustrate a series of points around lean software development or lean product management or lean product development as part of it. So hopefully you'll get something else apart from the story of building the Millennium Falcon. So this is the agenda. This is what I'm going to talk about today. I'm going to talk about, I won't talk about ThoughtWorks because that's too salesy, so forget that. I'll talk a bit about Lego. I'll talk a bit about Star Wars. And I'll talk a bit about flow, lean product development. So do a recap on Lego. Does anyone in the room not know what Lego is? That's my recap on Lego. Fine, good. That's pretty easy, that bit. We should probably do a recap on Star Wars. Has anyone not seen Star Wars? And there is always one. There is one. There you go. So, okay, you might want to go la, la, la. Unless you've deliberately avoided the whole thing, right? You might want to go la, 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 because there's spoilers in this. Incidentally, has Obi-Wan come out here yet? Oh, my God. Awesome. I was going to come on. If it has, I'm just standing there. Oh, hello there. So let's do a recap on Star Wars. Episodes 1 to 3, well, we don't talk about 1 to 3, right? So that's past history. We pretend they don't happen. We just forget about it entirely. Episode 4, well, this is the summary of the plot. Boy realizes he can do magic. It's pretty cool. Falls in love with a girl and sticks it to the evil empire. Now, did anyone notice the horrendous casualty figures in this? Tens of thousands of innocent stormtroopers died at the end of this movie. That's pretty... How can they be the good guys? Episode 5, Boy's mate gets frozen. Boo. Boy learns how to do magic. He finds out his dad runs the evil empire. That kind of sucks. Episode 6, Boy understands he loves the girl as a sister, which is quite lucky. Phew. Boy fights dad, dad fights boy, boy beats dad, etc., etc. Party. Ewoks. Episode 7, girl realizes she can do magic now. You can see where this is going. Falls in love with a boy, sticks it to the evil empire, something bad happens to one of the dudes. The boy's back, except he's old and grumpy. My God, Leia, no, not Leia. That's the main spoiler. And episode 9, what? Like there was a guy who was in the first, he was dead? Yeah, I'm all the Jedi. That's all you need to know about Star Wars. That's pretty much the entire plot of the 9 movies so far. Is that all clear? We've all got that? You agree with it, right? Yeah? That's fine? Okay, good. Okay, I'll do a brief recap on flow. So this is what I mean when I say flow. Flow of stuff, flow of work. I think it's the idea of system optimization, optimizing the entire thing, the system that you're working to keep stuff moving as fast as possible. I think I quoted Dan North yesterday when he sort of said, working to safely and sustainably reduce the lead time to thank you. That's what we're looking to do when we're looking to optimize flow. That's my definition. I will briefly introduce myself. This is me, clearly. I've been doing some writing recently on patterns of legacy displacement, so with 2 of my colleagues. So I'm sure people have come across the strangler vine pattern before. Now, if we talk about replacing legacy software or displacing legacy software, everyone always says, oh, we'll use the strangler vine pattern. Everyone nods sagely, yes, we will use the strangler vine pattern. And then, what the hell does that mean behind the kind of hand? Because there's actually quite a lot of stuff that you really need to kind of understand if you're looking to displace legacy systems. What does the strangler vine actually mean? What are the sort of technical and business patterns, analysis patterns and techniques you need in order to successfully migrate away from a mainframe or from a big monolith or from whatever it is? So trying to deconstruct things like the strangler vine and create a pattern language and a pattern library that we can use to communicate about displacing legacy. I'm also a massive nerd, in case you haven't guessed. This is me with my 13-year-old son at Warhammer World in Nottingham. We both like painting Warhammer 40,000 figures. And there's a lot of us about. Now, witness the firepower of this fully operational conference talk. Well, it's not a galaxy, it's an office, and I wish I'd licensed the music, so I'm sorry, it would be much more dramatic, but I don't have the music. A long time ago, in an office far, far away, lean Lego. Episode 4. Remember, we don't talk about episodes 1 to 3, right? Episode 4, a new box. So this is what the box looked like when it turned up in our office. You can see a few things about this box. The first is 16 and over. If you've spent much time building Lego, you know that they have age ranges. This is for people like me, adult friends of Lego. There's a name for us. That's quite sad. I have a lot of this at home. I was just talking with Lars outside. I can't see if Lars is in here, but just talking about the fact I've got the Apocalypseburg set from the Lego movie, and I've got the big pirate ship, and I've got the Ghostbusters fire station, and all sorts of cool stuff. But anyway, this is the Millennium Falcon set, the original Ultimate Collector's Edition Millennium Falcon. So another few things you should know about this box. It's a 300 double-sided page manual. There's quite a lot of instructions in this. This is what this looks like. And about over 5,000 pieces. At the time, it was the biggest Lego set that they'd ever made. This is the team. This is my friends who got together. So we were in thought, because we're hippies, right? We call it being on the beach rather than on the bench in many other consultancies. So we were on the beach, like, enjoying ourselves in the London office before Christmas. And we thought we'll get together and we'll build this thing. I did promise it's not just about Lego and Star Wars. There's a bit about like what we do, how we do it, and how we can use some techniques and tools to make the way we do stuff better. So I'm going to introduce a few of these now, and I'll be using them to illustrate progress over the course of the rest of the talk. So I appreciate you will know some of these tools. You will have seen some of them, used some of them, probably use them on a day-to-day basis. But I like introducing them because it calls attention to the fact that they're there for a reason. We use these tools for a reason, not just because we have to use the tool. And what do I mean by that? Well, I'm sure lots of people in this room, when you're building software, you might use a story wall, right? Or a Kanban board. Maybe it's in Jira these days. Maybe it's physical, like in the before times, like this. Who uses a story wall in the room? No, everyone, not everyone. No, actually not everyone. Most people just can't be bothered to put your hands up, right? Fair enough. I've got your numbers now. I'm watching you. So this is a story wall. So why do we use story walls? Why do we visualize work? Well, as I said yesterday, the reason it's important for us to visualize work with what we do is because the work we do is invisible, right? It's in people's heads. It's in the person who comes up with the requirements head. That turns then into something that is maybe on in a Word document, a business requirement document, gets elucidated into requirements, which gets turned into something that we can work on. The reason we use these is if we didn't use these, that work would be invisible. We wouldn't be able to see the stuff that was coming up. And as I said, if you're in manufacturing, it's a very different thing, right? It's a very different process that you go through, very different idea around managing inventory. Because if you're in manufacturing, you can see when stuff, or retail, you can see when you've got too much of a thing or too little of a thing, because you can look at it. Is there anything there? No. Well, we've got too little of the thing, right? Is there loads of stuff there? Then we've got too much of a thing. You can see when parts of your process are broken, right? Because you can look and see where stuff is building up, where you've got inventory building up, ready to be turned into widgets or something, right? We can't see that unless we visualize it. This is probably the biggest, I think, win from agile software development over the years, is visualization, visualizing work in progress, visualizing inventory, visualizing the amount of stuff that's in our system of work. Because what we can do then, using other tools, is understand where blockages are, where constraints in our processes are, understand where the system is broken down, and work to optimize it. So in these story walls, we tend to have swim lanes. We'll have, the simplest one is to do, doing, done. But you might have, ready for analysis, in analysis, ready for dev, in dev, ready for QA, in QA, ready for deployment, deployed, as a series of process stages that work flows through, in the same way that an orange flows through a series of process stages from Seville to my table. It just involves trucks and it involves warehouses and so on. But the same thing happens, physical stuff moving through a process. And I'll come on to the importance of these ready for stages a bit later. But the key thing to note is we have not just in dev, but we have ready for dev. We visualize queues in our system. So this is a build-up chart. ThoughtWorks, we try not to use things just because a process document says so. So we don't burn down like Scrum does, or generally used to. We burn up to total scope. So we understand how much work we've got to do, and then on a week-by-week basis, we burn up via velocity or counting the number of stories delivered, whichever is appropriate. This is a burn-up chart. Now this is where it starts to get a little bit more esoteric. Not everyone in the room, well, generally not everyone has come across cumulative flow diagrams, or finger diagrams, finger charts they're called. Anyone use these daily? That's a zero uptake on that. So the thing with cumulative flow diagrams, it's essentially taking your burn-up chart, or burn down, but burn-up chart, and plotting not just the total number of points completed, but the total number of stuff done per stage on your board. So what we're seeing here is each of the colored areas represents a swim lane in the storyboard, if you like. And what this allows you to do when you use these is to identify constraints in the process. So you can see, for example, We've got this pink thing down the bottom here, this pink area, which represents the amount of work that's been showcased. So at some point here, we had a showcase, and then loads of work was fine, signed off by our PO, but then there was no showcases for ages and ages and ages and ages and ages. And loads of work was building up and building up and building up until we finally had a showcase again and these deployed stuff. So you can start to identify blockages, constraints in your process using these. Value stream mapping. There was a talk yesterday. Unfortunately, I was a bit exhausted and sort of adrenaline filled after my opening talk. I missed the talk on flow engineering. But I know they talked a lot about this because I sort of glimpsed it through the window. A value stream map, very simply, is where you track the activities within the process and how much time on average they take to perform. You get two different types of activity. In this case, you've got value-adding activities, which are the top bits, 3 days, 1.5 days, and a half day. So you can imagine this is 3 days of development work. This is actually from a client, 1.5 days of testing, and then half a day of deployment. Value-adding activity, taking the thing, turning it into something that's more valuable via writing code, writing tests, and deploying it. And then the bits that are kind of like the down steps, as it were. There's probably a name for that in maths. Where you've got 2 days, 10 days, and 30 days. These are wait times, so times waiting between value-adding activities. So even though you've got 3, 4.5, 5 days of stuff that's adding value here, 5 days of adding value, how long are you waiting? You've got 2, 10, 30, 42 days of work just sitting there not doing anything. What's the problem with that? Well, because that stuff, that requirement could be in money. Sorry, could be in production making you money. There's a concept from lean product engineering called the cost of delay. Now, I like this idea of the cost of delay. The cost of delay is, I kind of think of it as like a game show. When someone doesn't win the prize on the game show, and they're like, oh, poor you didn't, look at what you could have won. And it's like a boat or a car, but you didn't win it, right? So you're like, oh, God, didn't win it. The cost of delay is the same thing. It's how much money you could have made if you'd got the thing into production earlier. Now, if you reduce some of these times on here, reduce the 30 days between testing and deployment to 1 day, then you've got 30 times more money you could have made out of that one particular requirement. So value stream maps are really, really important, like a really useful way of identifying what's going on in your system, identifying where your constraints are, where your blockages are, and where you can reduce waste, essentially. And generally, just by plotting these things out, we're all smart people. When you take a look at something like that, your first reaction is like, why does it take 30 days to go from here to here, right? What happens if we shrink that? Can we deploy to production every 10 days, every week, every 5 days? Can we do it every 1 day, say? And often, just by analyzing the wait times in your processes using value stream maps, you can improve throughput, you can improve the amount of work you get through into production by orders of magnitude without doing anything else, just by trying to work on wait times. This is another rather more esoteric one. So this is a control chart. So instead of plotting number of stories cumulatively, or velocity cumulatively, like in a burn-up chart, this is where you plot basically velocity and work out what the average velocity is over time. So there's a fact within systems engineering, as in control systems and things, right? Where from manufacturing, where essentially you don't look at individual process steps. You look at the system as a whole over a period of time, because every system has an inbuilt variability. Every system, even machines, are variable. Sometimes they'll take 1 minute to produce a thing. Sometimes it might be 1 minute, 10 seconds, sometimes 90 seconds. So by tracking the variability of your process steps, you can understand what's normal. Right, so how many of you have been in that situation where you've been, plodding along, doing quite nicely, you've done, a number of story points, and then the next week you do, there's a really gnarly requirement, really gnarly user story, and it doesn't quite get done by the end of the sprint. And it follows on to the next sprint. And so suddenly you're doing way, way less user story points, maybe half. And your manager goes, why have you done, well, you should be working harder, or something, But actually, if you start plotting these things on control charts, what you understand is, over time, that's just what the system looks like. You're going to have a natural variability of how much work you get done every week. And then the important thing is these upper and lower control limits. These are 3 standard deviations either side of the mean, right? So you can plot this, and then when you have exceptions outside the control limits, you can then investigate. Why did we do 50 points this week when we only did 10 points last week? That's way outside our control limit. Or why did we do nothing this week when we did 10 last week? That's outside our control limit. But if it's between the control limits, that's just your system. There is no point. That's just how the team is working. Interestingly, this is where Six Sigma comes from, if you've come across that lean methodology. Six Sigma comes from control charts and 3 standard deviation sigmas either side of the mean production rate. Okay, fine. You're like, teaching your grandmother to suck eggs. No idea if that translates into Danish, but I'm teaching your grandmother just to suck eggs in English. And we'll get back to actually the process of building the Millennium Falcon. And I promise you, this story actually happened. This story did happen. We didn't use all the tools at the time. I might have retrospectively cast what happened into the tools, but this did happen. So the Lego strikes back. So first of all, what happened is we all looked, 5 of us took a look at this set of instructions, and we're like, oh, this is really, really cool. Look at what's amazing, all these like knobbly bits and Lego Technic bits and stuff. And then we all jumped into the box and found all this stuff, and then we all put stuff together, right? We all just put the bits together. There's 5 of us all like, yay, super excited, more Coca-Cola, whatever it is you're drinking, more coffee. And the thing is, doing that went really, you're having fun, but it went really, really slowly. The amount of time it was taking for us to get anything done, it just took a long time. Everyone's searching for these things, everyone putting it together. It went really, really slowly. And it turns out this is what the value stream map for our system looked like. In fact, this is what the value stream map for the system of building Lego looks like, right? So you have a value-adding activity, which is finding bits, sourcing inventory, and then you have a value-adding activity, which is putting those bits together. So you have finding pieces and you have assembling pieces. And it was taking ages. And that's my first tip, right? Use these tools. They're there for a reason. They're not just kind of, there for consultants to kind of show you shiny pictures. They're actually super useful for understanding the system in which you work. Understanding where your value-adding activities are and where the wait times are in between those value-adding activities. So understand the system you're working in. And what was happening is we were processing our work serially, essentially. Everyone was finding stuff, and then everyone was putting stuff together. So there's 5 of us finding stuff, 5 of us assembling stuff, 5 of us finding stuff, 5 of us assembling stuff. Woo, it's exciting. Look at all this Lego, it's amazing. That's the second tip, right? You use these Kanban boards and story walls to visualize your system. Right? They're there for a reason. It's not just so you can have a nice shiny Jira wall that you can show your management team, right? The reason we have these things is so as a team we can understand and analyze how work is getting done, how flow is happening, how requirements are flowing through from idea through into thank you. So you use these things to visualize your system, to make the work visible. So what was the result of this? Well, the result of this, well, it was going slowly, as I said. And in fact, we worked out using a burn-up chart that we were going to take until the heat death of the universe to put this thing together. Now, we're in professional services. We, us meatbags or invariant terminating units or whatever you want to call us, we tend to have to bill, right? That's what our job is. We're on client site building software for people. And asking for 5 of us to wait until the heat death of the universe in order to build the Millennium Falcon was probably not gonna fly with our leadership team. You can tell how old this is. It's pre-meme, but it is after emoticons, which is good. So boo. Episode 6. The return of the process Jedis. So a funny thing happened. This is our system of work, right? These are the value-adding activities, finding pieces and assembling pieces. And so, as I said, we started off with everyone doing one thing and then everyone doing the following thing. So everyone finding stuff and everyone assembling stuff, in sort of serial. We started doing something else. We started to specialize. We started to have some people finding bits in advance of some people putting stuff together. So, and they were doing this at the same time, just one in advance of the other, much like BAs are working on user stories or doing analysis in advance of developers picking up a piece of work, or developers finish a piece of work before QAs are doing exploratory testing. We had different people at different stages of the process. See, there you go, that's us doing it. We had some people looking for stuff, some people putting stuff together. So what we did essentially was identify a constraint. By understanding where we were going slowly and why we were going slowly, we identified a constraint in the system of work. I don't know if anyone in the room has come across the more modern version of the goal, but the Phoenix project, which is a business parable about the theory of constraints and optimizing systems, essentially, which is based on an original version called the goal, which is about lean manufacturing by Eli Goldratt. And in the goal, Eli Goldratt identifies this called the theory of constraints. What the theory of constraints says is, in any system of work, originally manufacturing, there will always be a constraint. There will always be a constraint, a bottleneck that you can identify. Right? So what we should do in order to optimize our systems is to work to identify what the constraint is, identify the bottleneck. Then I think the exact phrase is subordinate everything else to the bottleneck. So if you've got a machine and the machine is the bottleneck, you basically make the machine go as fast as you possibly can. And then when the machine is going as fast as you possibly can, you can't really do much else, right? Because the machine is going as fast as you possibly can. You might add another machine, or that might be an option to do. But generally what happens is the machine is going as fast as you can, now move on to the next bottleneck, and then the next bottleneck. That's the theory of constraints. There's a great story from the goal around scouting, if anyone's read the goal. But Eli Goldratt uses the story of scouts going on a hike to illustrate this. So he says, you've got a scout troop and you've got one member of, maybe there's 10 scouts, you've got one member of the scout troop who's a bit less fit than the others, but they've also rather stupidly packed like loads and loads of stuff. And everyone else is just carrying a bivvy bag. This one scout has got, kind of pots and pans jangling off them. They've got loads of really heavy food and water and all sorts of stuff. And they're going really, really slowly. And so what happens is, the scouts at the front are going faster, and there's this poor scout at the back who's getting further and further behind. That scout is the constraint. So how do you solve that problem? Well, there's a number of ways you can solve the problem. In the goal, Eli Goldratt says what you could do is you can identify that the fact the scout is the constraint. You can work to minimize the amount of weight that the person's carrying, right? So they might walk faster if they haven't got all these pots and pans. So you distribute all the pots and pans around with the other scouts. And then you try again, and they go a little bit faster, but they're still quite slow because they're quite unfit. The end result of the story is what you do is you put the unfit scout at the front, and then all the other scouts behind, and then you all walk at the same rate. The system operates at the rate of the lowest performing member, essentially. And that's the theory of constraints. And what we did in this is we identified this constraint. It was around, these bottlenecks around finding people, finding things. And it turns out you can find pieces in parallel, right? It turns out there's lots of stages of the manual on each page. So some people could find pieces for one bit of the manual, and then some people could find pieces for the next stage of the manual, and some people could find pieces for the next stage of the manual. You could work on all these things independently from one another and build up this backlog for the people who are putting Lego together to work on. So use the theory of constraints. That's the next tip. Use the theory of constraints. So the next thing is this, I mentioned at the start, this idea of queuing theory. Queues. Queues are everywhere. Queues are the root of most evil in most processes, in fact. I said there's a great book yesterday called Principles of Product Development Flow by Don Reinhardtson. This blew my mind when I read this book. I read it, I reckon about 2009, maybe. Dan North, if you know Dan, so Daniel Tilhorst North now on Twitter, he recommended it to me and I read it. And I was like, oh, that's kind of interesting. It's very dense. It's like 280 odd principles to improve flow, right? To improve how work flows through systems. It's quite dense. I thought that's kind of okay. That's interesting. But then I read it 10 years later. I read it back in 2017 because I was going to Australia to a conference and Don was keynoting. I can say Don because I know him. I met him. It's cool. And he was keynoting, so I thought, God, I better read his book again. I read it on the plane on the way to Australia, and it literally blew my mind. I'm like, why didn't I get what I got out of it like 10 years ago? And it's because I think the journey I'd been on over 10 years meant that I was able to take so much more from it. All the questions I'd sort of had about the difficulties of managing processes and teams, he seems to have answers to all of them in this book, right? And even better, he has economic answers to these things. Why should we do this particular thing? Why should we change the team shape? Why should we change our process? Why should we optimize for smaller batches and do continuous delivery? If you've ever had to convince someone to give you budget to improve your build pipelines so you can release software more quickly, Don has got the economic argument for why that will make you more money. And that's super, super interesting if you're trying to convince people who are interested in finance about why they should give you some money to do stuff. It blew my mind. And in this book, Don spends a lot of time talking about queues and queuing theory. So what do we learn in QS in Computer Science 101 about queues? Well, we need to manage queues quite carefully. What happens in a messaging system if queues start backing up, right? Queues start backing up, you've got lots of messages that are just sitting in a queue waiting to be processed by a consumer, maybe competing consumers. Well, what you can do is you can add more consumers into that process, right? I don't know if you remember from queuing theory, but what you have is the idea of a number of you have basically a number of processes or services that are processing messages coming in from a queue, and then they output a number of messages as well. That's basically, you have this, and the number of messages coming in versus the number of messages coming out is a measurable rate you can look at. But the problem is when you back up queues, when you get messages sitting at the bottom of a very big queue, well, obviously that message will take longer to process than if you've got a message at the top of a queue, right? So whenever you've got queues of stuff and the queues grow, what happens is essentially your cycle time increases. The lead time for the thing to be processed gets blown. So if you think about work, we've got a Kanban board. Has anyone got like one of those sort of defect boards which has got like 5,000 defects on it? Right, that's kind of classic enterprise kind of thing, where you've got 5,000 defects, and like you're never going to get through any of them, right? Even if you spent from now until the end of your career, you'd probably only put a dent in a little bit of them, because you're trying to process a massive queue and process a lot of work off a massive queue. Dan North has got a fun trick. When he turns up in consulting mode, he often just deletes all that. Because if they were important, they would have been done already, right? So just delete it all. Delete all that stuff you haven't done yet. But the funny thing that happened is that we started to create natural queues, essentially. There were natural queues as part of the manual. So the people finding bits started putting bits on the picture, and then they put bits on the next picture, they put bits on the next picture. So we started to build up like a ready for assembly queue. So we visualized this queue in the system, this idea of pieces that are ready to be assembled based on the pages in the manual. And then the folks assembling pieces, assembling the Lego, putting the Lego together, they started pulling from the queue. So we were finding bits, pushing into the queue, and then we were taking stuff from the queue. So this idea of visualization, which runs through this whole thing, visualizing work in progress, visualizing queues in particular, is kind of a key. Because when you can identify where the queues are, you identify how deep the queues are, how much stuff is in the queues, you can basically managing that, visualizing that helps in maximizing throughput. And I'm going to give you a quick example of that here. It's also a leading indicator, queue size, of how quickly you can get stuff done. So 4 key metrics. Lead time is one of the 4 key metrics. It's not a true lead time, but lead time as defined in the door of the state of DevOps reports and in Accelerate is from developer committing a line of code to that code earning money in production. Right, it's the lead time to value for that piece of code. Right, so cycle time here, that's what we're talking about, lead time, cycle time. Again, it's quite funny. The reason I sort of say it's not really lead time is because lead time would be from when the requirement was defined all the way into production. requirement defined all the way into production, not this little bit of it at the end. Because you can imagine being infinitely quick, infinitely fast. You could be an infinitely fast developer team that took zero time at all to get code from commit into production. But if it took you 8 months to get the requirement to that point, like you've still got an 8-month wait before you make any money, right? So kind of that little bit of it is kind of interesting, but not the whole story. Anyway, the point is, if we want to minimize cycle time, we want to make stuff flow through our system more effectively, more quickly. And one of the ways we can do that is by looking at leading indicators for cycle time, and queue size is one of those leading indicators. Now, I'll illustrate this with an example from conferences that you might be familiar with. So say we go to lunch at 1 o'clock in the afternoon. It's lunchtime, I'm going to finish the talks, yay. There's been a bunch of people who haven't been in the talks, right? So there's going to be some people who are kind of just milling around, maybe in the expo area, maybe upstairs on the second floor, whatever it is, and they're going to kind of go to lunch, and then all of a sudden, the session's finished, and a ton of people go to lunch. This is basically your arrivals into your lunch system from conferences, right? So you've got an arrival state where you've got a sort of steady number of people just turning up, a ton of people suddenly turn up, and then you've got a bunch of, a steady state of people again turning up. This is departures. This is the capacity of the system to serve you lunch. It's a constant capacity, right? There's a constant amount of people who can be getting lunch at any one particular point. And it's slightly delayed from the people arriving. Yeah, that's the amount of time it took them to serve lunch, but these are the departures from the lunch queue, as it were. So sessions finish, a ton of people arrive. Essentially, the length of time it's going to take you if you arrive at the queue here, right, the cycle time is this difference over here. So if you arrive halfway up this thing, it's going to take you bloody forever to get lunch, essentially. Whereas if you're down here and there's no queue in front of you, it's not going to take you very long at all to get lunch. Essentially, what we can do, because this vertical axis, this is queue depth. By measuring queue depth, how many people are queuing for lunch, not how long is it taking them to be served, we can work out cycle time. And by controlling queue depth, we can control cycle time in advance, which is super interesting. And actually, NDC normally, if you've been to Oslo or to the other conferences, what they normally do is do lunch continuously throughout the day. They have little stalls everywhere. So you go and you can just pick up some lunch at 10 o'clock in the morning if you want, or 3 in the afternoon. It's continuous lunch service, which fixes this problem. Because what you have, in fact, is the continuous arrivals and departures, minimizing cycle time. But this is the importance of queue size. And by visualizing queues, we can basically work out what our cycle time is and how to control cycle time and how to improve our cycle time. As a result of all this work that we did, we got faster. See? So now we're into a number of hours, how quickly we can put the Millennium Falcon together, which is good, because 48 hours, that's what, if we're doing 40 hours a week, just over a week's worth of work, that's good. We can actually get it stuff done before Christmas. Excellent. That's my next tip. We can use burn-up charts, and as we see here, yesterday's weather to track progress. So what does yesterday's weather mean? You've probably come across this from Agile. It's, if you look at what's today's weather going to be like, well, 70% of the time, it'll be the same as yesterday's weather. So how much work are we going to get done this week as a team? 70% of the time, it's probably going to be about the same as we did last week. And you can use that to essentially estimate when you're going to get stuff done, roughly within orders of magnitude, 50% either side or something. So use burn-up charts and yesterday's weather to track progress. But we didn't stop there. Other funny things started happening. And I repeat, this did happen. All of this did happen. The team became T-shaped. Now, I'm sure you've come across this idea of T-shaping, right? Generalizing specialists. I'm very deep in Java, mainly Java, that was most of my career, but I've also done a bit of Scala, a bit of Clojure, I've done some C#, tiny bit of F#. Didn't understand it. Wasn't that a joke from yesterday? But also distributed system design, software architecture. I can, at a push, pretend to be a business analyst, right? At a push. I can pretend to be a QA for a couple of weeks, then I'll get found out. But my depth is in Java, is in software architecture, and the technical side of what we do, more technical side of what we do. And that's what we mean by T-shaping. We want people who can act in different roles according to need, right? That's a way of optimizing our process again, optimizing our system. So what we ended up with is a couple of people who were specialists in putting the Lego together and a couple of people who are specialists in finding the bits of Lego. And it probably is kind of obvious why, right? And if you're putting stuff together, it's a big, complicated, topological puzzle, essentially, building this thing. And it's quite hard sometimes. It says 16 plus on the box. It's quite hard to actually understand how the bits go together. But the more you do it, the easier it is, I kind of see where this is going. I can put this bit there and then this bit there and that there. Similarly, if you're looking for stuff and you've got some little bit to find, I just saw that a minute ago. I'll just go and get it. You get quicker, you get more effective in your role as you specialize. But it didn't mean that the people who are finding things weren't able to put the Lego together, right? They could still put the Lego together as well. And the people who were putting the Lego together could still find things. And those specialists noted this. This is a control chart. This is the amount of time it took to find pieces. What you can see here is tremendous amount of variability in this process, right? Sometimes it's taking 0 time at all, or hardly any time. Oh, there it is. Sometimes it's taking loads of time. What the hell is that little thing? Lots of variability. It turns out that when you've got a big set like that and all the bits in one place, finding a piece is a function of piece size and the total number of types of pieces that there are. So if you've got a big thing like that, it's a lot quicker to find, and you've got lots of them, than if you've got one tiny thing out of 5,000. Right? So it's inherently variable. So how do you fix that? We started just in time grouping like bits of pieces together. We started creating little sort of inventories, sub-inventories, if you like, grouping little bits so that we could go and immediately find stuff. But what we didn't do is do it all up front. It happened sort of just in time as part of the process. And that meant that the variability massively reduced. Right? The variability of the system, we identified that there was variability in the system, and how can we fix the fact that it's taken ages to do this? Well, what happens if we just put these little bits in little plastic cups? We got a lot faster again. So that's the next thing, this idea of control charts, understanding variability, understanding what your normal system looks like, what the normal variability of your system is, and working around exceptions, identifying when there's been an exception, working to understand why. Why did that story get blocked for 3 weeks? So we tanked on our progress. Or why did we go so fast this week? What was it about this particular set of requirements that enabled us to go so quickly? And then working to understand the variability and reducing the variability. There were other fun things happening too. This is a real defect card that we had from the project, I say. We actually did bug tracking. We had different types of bugs as well, 2 different types of bugs. We had cosmetic bugs and we had proper defects, if you like, so P1s, or stop the line, broken build bugs. You can kind of see now, if you've got something that's like just going to make something look a bit shinier, then you can defer. We'll raise a bug, can't find the piece. We'll raise the bug, stick it in our bug tracking tool, which is the table next to us. And then, when we find the piece, that's fine, we'll just stick it on. But sometimes there was a structural element that we couldn't find. At that point, red build, everyone needs to swarm to break the build, to fix the build, right? Pull the and-on cord from Lean. Right, the whole team needs to find this bug. So there you go, non-critical. This was a cosmetic type of bug. We also had work-in-progress limits, natural work-in-progress limits. We limited the amount of work that was ready to be done. Because the ideal with Lean product development is this, or in any Lean process, is the idea of single-piece flow. Right, so a customer asks for a requirement, and that requirement flows as a single piece all the way through into the customer's hands. This is the famous piece from the Toyota production system. Where, ideally, if I order a Toyota car online, that one order triggers all the processes behind it that lead that particular car to be built just for me. Single piece flow throughout the entire system. And the way you manage single piece flow, or one of the ways to help with single piece flow, is by limiting the amount of work the amount of work in your queue. So limiting queue depth, having work in progress limits. And there's another way in a minute. But can you spot how We limited the natural way to limit the amount of pieces that had been found ready to be assembled. We've got someone in the front. Yeah, by the pages in the manual, because you could only put so many pieces on it before you had to turn the page, which flipped all the Lego all over the floor. So we had this natural, like, work in progress limit based on the queued steps of pieces that had been found and placed on the manual. And the other thing we did is swarming. So because we have T-shaped people, we can both find stuff and assemble stuff. If we were blocked, because that we can't turn the page, we've found all the stuff we need to find, then those people finding things can help put stuff together. But the key thing is you swarm upstream. If you're a developer in a development process, you help the QAs out. Ideally, if you're a BA, you swarm and help the developers out. You swarm upstream to improve overall throughput, optimize the system, not just your little part of the system. Don't sit there, well, I haven't got any work to do now. As much as that might be nice. Sometimes that's nice for a break, but often you might be able to go and help the QAs who are like, oh my God, there's so much to do. And you can pretend to be a QA for a bit, right? So tip 7, limit work in progress and then pull more work from upstream. So you help the people out upstream of you. You help getting work through the process into production, stopping the blockages. Because the reason you have blocked work in progress is because there's a blockage upstream that you can't start. So here we go. We actually finished it in about 24 hours, this thing. And then the memes started, so you can tell where the new talk starts. Chewie, we're home. Rah! There's the Millennium Falcon, or the old one. There is a new one. The new one is so big, it comes in a box with wheels, and that's true. It nods, yeah, so big you needed like a trolley thing. It's pretty astonishing. And unicorns. So where are we so far? My conclusion so far from the tips and so on. Understand your system. So use the tools available because they're there for a reason. They're not just because, it's not just a cargo culting process or mechanism we go through to get stuff done. These tools are there because they help us improve visibility. They help us understand where queues are in the system. They help us to understand where we can use the theory of constraints to identify bottlenecks and unblock them and so on. Right? So use the tools. Visualize work, right? Make stuff visible. Make the invisible stuff visible. Work to continually identify constraints. Use the theory of constraints. These idea of things like queues, whip limits, swarming, they help keep they help keep throughput high. So what do I mean by that? Well, these things, they help us get towards the goal, the ultimate goal of single piece flow. One thing moving all the way through, unimpeded from idea or customer want through into customer thank you. And then use these other visualizations tools to understand when you're going to be done, when you're going to finish. Of course, if you're in product development, you're never going to finish, are you? But there we are. And then use control charts to identify and reduce variability in the system. So that's where I sort of stopped about, wherever it was, 8, 10, 9 years ago. That's where Lego was, that sort of time ago. Then I was asked to do a keynote for our ThoughtWorks conference, XConf, which is a really fun conference, actually, about 3 years ago, I think. And I thought I'd do a redux on this because, I've learned a lot since then. I've learned a lot about how to manage work and the importance of things like queues and so on. Lots of stuff has happened in the industry, right? Microservices has happened, for example. All these kind of interesting ideas around decoupling and how you can scale more people around problems and so on. So what would Lego have learned in that period of time? Episode 7, 8, 9. They're like 4, 5, and 6, but just a few years older or newer. Hi. So this is the only time I was able to go and expense a Lego set, which I did. It was great. I went and I bought a Nexo Knights, because my kids were loving Nexo Knights at the time. I bought this Nexo Knights set. You can tell this isn't as complicated. This is only 9 to 14. I should have got a bigger one, but you can't push your luck too much, can you? So I got this Lego set. And I thought, what would Lego do? So I'll ask the question. If you, 10 years down the line, if you were Lego and you were also constantly learning from the experience of building Lego, what would you do? What would be the change, the biggest change that you could make to have the biggest impact on the Lego system of work? And I've got someone with a yellow t-shirt with a hand up. Yes, please. Bags with numbers. And there's an interesting reason, a scientific reason why that works. So remember I said at the start, we've got all, basically the old Lego sets used to have all the pieces in one big bag, essentially. They were grouped into maybe sub-bits, but more or less just all the bits in a box. Taking ages to find stuff. You have to group stuff together. You're having to create these little bits of inventory as we go to improve our, to decrease variability and improve throughput. Well, this is from the principles of product development flow. The batch size queuing principle, reducing batch size reduces cycle time. Right. The single most important thing you can do when optimizing a process in terms of improving throughput is to reduce the batch size, is to reduce the number of requirements being pushed through into production, right? For example, that's what we mean by batch size. When we talk about continuous delivery, right, continuous deployment, what we mean is, really, we're going to work to reduce the batch size to 1. So we can push a button, 1 requirement goes into production. As opposed to waterfall, where your batch size is maybe 100%, right? Your batch size is all the requirements which move as one batch through your process. And then all of them get tested, all of them get put into production. Continuous delivery is about reducing batch size. That's why it's so successful. That's why it works. And again, in another graph here, so batch size, queue depth, and cycle time, there's a relationship. Essentially, if we look here, this is time, as you can see. This is the number of stuff getting done, right? So if you've got a batch size which is 50% of the stuff, it's going to take that amount of time to start earning money on a requirement. But just by reducing batch size, you can get stuff into production, get stuff earning money way, 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 way faster. Average queue size proportional, blah, blah, blah. Little's formula, it's maths from queuing theory, actually, one of the most famous formulas from queuing theory. Don Runnison goes on to say, batch size reduction can enable us to shorten cycle time, often by an order of magnitude or more, without changing capacity or utilization. You can improve your cycle time by an order of magnitude without adding people or without having them work faster or harder. That's pretty cool. And that's the root of continuous delivery, right? That's what we should be optimizing for reducing batch size. I mentioned this book a number of times, but he talks about the effective queues here. This is essentially, queues represent batches. And queues create longer cycle times, increased risk, blah, 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 blah. Essentially, queues, big, deep queues, lots of stuff waiting for something to happen to them, big batches of stuff sitting doing nothing equals bad. If you take nothing away from this talk, take that. Here come the bags. So what Lego did was reduce the batch size. They basically, they say, okay, for the first 10 pages of the manual, you'll use bag 1. It's a smaller batch. For the next 10 pages, use bag 2. So it means you're reducing the variability. It takes much, much quicker time to find stuff. You can build stuff much, much, much faster. There's another thing they did as well. This is another principle from Don's book, the fluidity principle. Loose coupling between product subsystems enables small batches. You can build bits independently from one another. You can have multiple people building entire subsystems of these Lego sets, and then you can plug them together at the end. Does that remind you of anything from what we do? Pretty much the movement towards cohesive services around business concerns, right, that communicate via uniform interfaces. That's the fluidity principle in action for software architecture. And there's the finished thing. So my final set of conclusions is, first thing is understand the system, visualize it, use all the tools I've talked about already. Visualize queues. This is what I've learned, is that queues are the most important thing to understand. Where are the queues? How deep are the queues? How long does it take something to get from the bottom of a queue to the top of a queue? Identify constraints in your system. Use the theory of constraints. But you have to recognize its limitations in product development. I mentioned earlier the scout idea, right? How do you optimize for getting the scout troop to the end of their hike altogether? in the theory of constraints, they're talking about manufacturing processes. He's talking about machines. He's talking about optimizing machines. Machines can only do one thing. As we've sort of seen, we can do more than one thing. We can be generalizing specialists. We can adapt. We can turn our hands to other things. We are human beings, not machines. Sounds like a bit of a call to arms, doesn't it? We are human beings, not machines. So another example in Principles of Product Development Flow, he says, instead of the scouts all walking behind the slowest and getting there at the same time, why don't you send some of the older, faster scouts on ahead? They can like build a campfire, right? They could chop some wood. They could do useful value-adding activity whilst the rest of the troop catches up. We can do other stuff. We can swarm. Using work in progress limits and swarming helps keep throughput high. Small batches directly impact cycle time. And this idea of anti-fragility, building components, building smaller things that can integrate together, it's smaller, cohesive, decoupled components that can integrate together. So these are the sources from this. As I say, this did happen. Generally, that process of building the Lego set did actually happen, and we did go through all those optimizations. I've used the tools and the visualizations as a mechanism to describe and explain some of the ideas behind what we do in product development, what we do as software developers, and how we can use some of these ideas to optimize our processes. So finally, software should be cheap to replace, quick to scale, resilient, and it should allow us to go as fast as possible. The processes that we build to build software should allow us to optimize for flow and go as fast as possible. So the question is, what would Lego do? That's what you need to ask yourself. And Lego, they would use small batches. Control batch size, that's the key. Thanks very much. Enjoy the rest of your day. I'll be around. If you have questions, please come up or, yeah, cool. Cheers.